Hi folks, and welcome to lecture 10. In this lecture we're going to be analysing reciprocal functions. First, just see where we are in the module. We've looked at linear, quadratic, cubic functions. We're now looking at reciprocal. We'll look at these functions and then we'll do some analysis. Main thing to note so far is up to date we've been looking at positive powers on the input. Now we're going to take a look at a function that has a negative power on the input. Some of the features of the reciprocal function: simplest equation, the general equation. We'll be using this shortly. This is our typical hyperbolic curve. In the real world we normally just see that bit. One input, one output. Negative power on the input, and then we just have to watch out when the denominator becomes 0. When the bottom bit there is equal to 0, that's where we get this effect here, the kind of black hole. So examples of reciprocal functions in science: Boyle's law. Pressure and volume of a gas have a reciprocal relationship. Speed and time have a reciprocal relationship for a fixed distance. Frequency and period of a wave is very important for engineers. Perpendicular slopes have a reciprocal relationship, except it's negative. And unit conversions depend on reciprocals. We saw this last year. So generally they're written like this. We have our input below the line. That's what defines a reciprocal, that the input is on the denominator. This is the typical curve, the hyperbola. Just to see what happens when we square x on the bottom, we won't be doing any work with this, but this is also a reciprocal. It's a squared reciprocal. Just looks like that. All the outputs are positive, because you can't, even when x is negative, when we square it, the outputs become positive. But we won't do any more other than just have a quick look at it. Now we're just going to do a little bit of math. So asymptotes really are where the curve is. So if we were to draw the curve, there's always this point which the curve doesn't touch, and you can draw a straight line down. So that's the asymptote. So there's a vertical asymptote and there's also a horizontal asymptote. Now my graph isn't great, but I'll just show you how to find them first. We'll just take a look at them first. Sorry. This is the curve. And there's the vertical asymptote. It's where we could draw a line where it doesn't touch the blue line, the blue curve. And here's the horizontal asymptote. So that's what we're looking for. Where do these occur? So I'll just show you how to do it, that if you don't have the graph, we're asked, well, if I give you this reciprocal function, can you find the asymptotes without the graph? It's easy when you have the graph. So what we do is we say, well, really we're always interested in where is y equal to 1 over 0. In this case, in order to get y is equal to 1 over 0, then that must mean that x minus 2 is equal to 0. This bit on the bottom we just make equal to 0. So then x is equal to 2. So what this is telling us, when x is equal to 2, that's a vertical asymptote. Now the second bit is a little bit trickier. What we actually have to do now is isolate for x. So remember our formula manipulation. We want to get x on its own. And it's always tricky with reciprocals because x is always part of a denominator. That's the definition of a reciprocal. But the maths usually isn't too bad, because if we remember, I've shown this a few times, if you have a fraction on both sides, just a simple fraction, you can swap across the diagonals. So we can swap the 8 and the 1. And you can see that it's still actually a valid statement. So if you can do it for numbers, we can do it for reciprocal terms. So I'll show you what I mean. So we found our vertical asymptote. That's usually the easiest. To find the horizontal asymptote just requires a little bit of maths. So we have y is equal to 1 over x minus 2. And now what I'm going to do is I'm just going to write this, just tidy this up a bit, it looks a bit messy. Instead of writing it as y, I'm going to write it as y over 1. So now I have that scenario I just showed you with the half is equal to 4 over 8. I can swap across the diagonals. There's no harm to put brackets around there just to keep things a bit tidy. So now when I swap across the diagonals, I'm going to get the bit in bracket comes up to where the y was, and the y moves down below. And this is over 1. So now we've got x minus 2 is equal to 1 over y. We can tidy it up if we want, but we do actually have what we need, plus 2. So now we're saying, well, where are we going to get 1 over 0? When is x going to be equal to 1 over 0? We're not really interested in the 2 bit at the moment, but when y is equal to 0, when this is equal to 0, obviously we're going to have 1 over 0 plus 2. The plus 2 is irrelevant. Once we have this bit, it's an invalid statement. So we've kind of found the black hole. We've now found the y coordinate of the black hole. The y coordinate is 0, which is there, and that gives us our horizontal asymptote. So that's how you can find asymptotes mathematically. I'll just go and bring in the graph. It's all a bit messy, so I'll tidy it up. Like I said, it's nice and easy when you have the graph and it's nice and pretty. So we'll take a look at another one. Find the asymptotes of the function here. Well, first of all, I'm looking for where is y equal to 0. In this case, we're letting this bit equal to 0. So when, when 2x minus 8 is equal to 0, we're going to achieve this scenario here. We solve for x. So now we've got our our vertical asymptote, which happens somewhere at 4. X is equal to 4. Now, like I said, we have to do a little bit of maths. I'll just swap across the diagonals. We'll get 2x minus 8 over 1 is equal to 1 over y. I can tidy this up. So again, just similar to before, guys, I just don't want to keep repeating myself. I wrote it as y over 1, and then I swapped across the diagonals. Just to be clear, that's what happened there. Now this is just 2x minus 8 is 1 over y. I can move the 2x is equal to 1 over y plus 8. And finally then, it doesn't really matter, we can work away, I will keep going, but it's this bit is crucial. That's the only bit that's going to give us the 1 over 0. And without doing any further maths, I could end up with 1 over, just to tidy it up, just to be complete, I divide everything by 2. But it's this bit here. This is the only possibility that gives us a 1 over 0. Where is that going to occur? Obviously, when y is equal to 0. So we could have arrived at that conclusion pretty much from here. So now we know our horizontal asymptote, y is equal to 0. And now the curve is going to look something like that. But again, I have a nice tidy version of it here. I clear away all my maths. And there's my asymptotes. So we'll do one more, a little bit complicated, a little bit more complicated. This is now, remember the typical equation, y is equal to a over x minus c plus b. Remember the general equation. Sorry, I've got those the wrong way around. Forgive me. minus b plus c, and that's an a there, not a 9. It looks like a 9. So now the maths is still the same. The only thing is, though, be very careful. We can't swap across a diagonal immediately. Oh, I better not do that first, actually. I'm dumping straight in. So we've got this y is equal to 3. I'll take this one a little bit slow because it leads into where we're going next. So I'm looking for, again, this spot. Where am I going to get it? Doesn't matter as long as I'm looking for that 0 on the bottom. Where am I going to get 0 on the bottom of my reciprocal term? The 1 doesn't matter. Where are we going to get 0 on the bottom? It's going to be when x minus 2 is equal to 0. So we solve for x and we get x is equal to 2. So that's our vertical asymptote. We've established that that occurs when x is equal to 2. Now we need to manipulate, and it's going to be a little bit tricky, guys, because we don't have a simple fraction on both sides. It's not like this. We've got another bit as well. So we can't do that swapping just yet, but that's still going to be our aim. I'm going to get a single fraction on both sides. So first thing I need to do, I want to move the plus 1. So what I'm going to do is subtract 1 from both sides. So now, and now I can write this as a fraction. Now we've got a simple fraction on both sides. I can swap across my diagonals. X minus 2 is equal to 3 over y minus 1. Now again, I can tidy this up. I'll just get rid of this graph. It doesn't help. I can say, well, x is now 3 over y minus 1 plus 2. But again, it's the reciprocal term that counts. That's the one that's going to give me 3 over 0 in this case. That's what I'm always looking for. Where will I get this? It's going to be when y minus 1 is equal to 0. So when we solve, we get y is equal to 1. So I hope that makes sense, guys. It's really, we're looking for this asymptote. The asymptote lives whenever we can establish where can we get a 0 on the bottom of the reciprocal term. The other terms don't really matter. They do come into it a little bit, but they don't really matter in terms of once you've established your reciprocal term, you can then find out where will I get a 0 on the bottom. What y value in this case will give me a 0 on the bottom. So a little bit tricky, but you know, it's kind of, we don't do a huge amount of maths in this one. So again, now once we have the curve, it's nice and easy to find. X is equal to plus 2 and y is equal to 1. So now we're just going to push on. We're going to do a little bit more analysis, but now we're going to take a look. Oh, sorry, this is 2 for you to try. Question 10.1. So have a go, determine. Now I won't give you the graph. You have to do it the way I showed you in the previous slides. And then question 10.2. So have a go at both of those. So just really, if you're stuck, just go back, watch the video and follow the steps and you should arrive at it. So now we're going to kind of work backwards. Is if I give you the curve, can you determine its equation? And it's essentially what we just did, but in reverse. So we'll take a look. The first thing I want you to do is identify the vertical asymptote, which is at x is equal to 4. I know my line is off a little bit there. It's hard to get the lines to move exactly where I want them to. My horizontal asymptote is at y is equal to 3. So I need those two bits to get started. Next thing, I need to pick any point on the curve, just as long as it passes through a nice easy place. So there's 3, 2. Oh, sorry. So there's 3, 2, and there's another point there if we wanted to use that. There's 5, 4. There's usually 2 or 3 of them anyway. There's probably another one, but I don't think that's quite there. So, sorry. But as long as you identify one point, we've enough now to establish the equation. So we've got our vertical, we've got our horizontal, and we've got a point. So just to give you a heads up, guys, from the equation, y is equal to a over, sorry, that's not a good a, over x minus b plus c. The vertical axis, asymptote, sorry, gives us b. The horizontal asymptote gives us c. And then we use the point, feed it in for x and y, and we can solve for a. So I'll take you through that now. So once you've established your vertical, your horizontal, and a good point on the curve, you're good to go. So this is just going over what I said. We're going to use this, the general equation, and we start to build the general equation of our reciprocal function. So the vertical asymptote, as I said, is equal to b. I should use this one. So now our function will look like this. We've now established b. Then we use the horizontal asymptote. Y is equal to plus 3. That's equal to c in the function. So now the function looks like this. And that should be an a there. Sorry, that shouldn't be a question mark. And now we need to find a. And how we do that is we use our point 3, 2. There's x and there's y. So we feed those in. So you can see there the 3 and the 2. And now we just solve. So here we're going to have 2 is equal to a over minus 1 plus 3. So that's 2 is equal to minus a plus 3. And when I do a little bit of maths, bring the a over to this side, becomes positive, bring the 2 to that side, it becomes negative. We end up with a is equal to 3 minus 2, so we get a is equal to 1. So now we can actually write out the full function. So it's fairly straightforward, but you just need to be a little bit careful at that last step in feeding in the x and y values and doing the bit of maths to solve for a. So we look at another one. Here's the curve. So first of all, what's my vertical asymptote? X is equal to minus 1. What's my horizontal? X is equal to minus 3. Pick a point. Now there's 2 points there. I'm going to use that second point, 0, minus 1, because 0 is always your friend when you're trying to work things out. To determine the equation in the same way as we did in the previous slide. So to find our vertical asymptote, x is equal to minus 1. To find the horizontal asymptote, y is minus 3. Find a point on the curve, which I identified. So now we're going to feed in the b value. Be careful with the minuses. B is minus 1. Sorry. I don't know why it's doing that. Very annoying. So just be careful. When we feed in b, it'd be negative. We now get this. The horizontal asymptote gives us the c value, so we feed that in. And now we're going to feed in the point. Remember, there's our x value, there's our y value, and we feed those in for x and for y. So now when we tidy this up, we're going to get minus 1 is equal to a over 1 minus 3. And when we solve out for a, we'll get a is equal to 2. Add plus 3 to both sides. So now we've done enough. We can establish the function because we know the three variables a, b, and c from the general equation. So you can guess what's coming next. There's just 3 of these for you to have a go. So there's the first one. So be careful, there's 3 of them, guys, so make sure you attempt all 3. I'll just mark in the asymptotes for these ones, for the first one, just to make sure you're set on the road. There's a point. There's another point. So that's just to help you get started, just in case you lose your way on the first one. Here's the second one. So have a go at that one, pause the video, make sure you work your way through it. And then here's the third one. So again, pause the video and work your way through it. So we just take a look, few examples of Boyle's law, of reciprocal functions, practical examples. Boyle's law, we talked briefly about this in the last lecture. So if the volume increases, then the pressure decreases and vice versa. The one thing though is the temperature has to be held constant. So we can see here that as the experiment goes on, the temperature is held constant. And there's various apparatuses that you can do. Some of them will change the volume and measure the pressure, like these ones. Other ones will change the pressure and measure the volume. So it's the same maths either way. Just you decide the input and then the output is measured. So if you're changing the volume, as in this case, then volume is on the x-axis. That's so important to get the axes right when you're drawing graphs. Input on the x, the horizontal, output on the vertical y-axis. Just a few, a syringe is a practical example of Boyle's law. As you increase the pressure, the volume reduces, and that's what forces the liquid out through the needle. If you've ever been diving, and if you go scuba diving, they would always advise you, if you get a bit disorientated, is just stay still, blow some air out of your tank, out of your lungs, and then watch which way the bubbles go and see where they get bigger, because they'll always get bigger as they go towards the surface because the pressure is reducing, so therefore the volume of the bubble of air increases. Gas storage basically is Boyle's law is essential for this, that we can compress gas safely, because otherwise it'd be very hard to kind of move gas around if you didn't pressurize it. It would be a very, very bulky and light material. And if you have to pop your ears at high altitude, that's also an example of Boyle's law, because there's a little volume of air trapped in your ear, and because the pressure in the plane is different to the atmospheric pressure, you need to kind of release the pressure inside your ear by popping them. From a more technical point of view, the frequency and period of a wave have a reciprocal relationship. Now again, this is very important from an engineering point of view, anything to do with sound engineering, like waves. So many things are driven by waves. We'll be looking at waveforms in the next lecture as well. We'll be looking at trigonometric curves. But we won't really do any more than just to say, well, the period is the time between peaks. The frequency is the number of waves that pass a fixed point in a second. So normally these waves, they look like they're moving. So if we could put a fixed point, we'd say, well, how many wave peaks passed in 1 second? That's the frequency, and it's measured in hertz. Another one that you mightn't be aware of, just if you have a cordless drill, not one you plug into the wall, but essentially it's got a fixed power pack. So P is a constant. So power of a drill is basically, there's two parts to it. There's the speed of the drill bit and there's the torque. The torque is the driving force. So if you're trying to drill, say, something really light like aeroboard, the speed won't change at all and there'd be very little torque delivered. So you could have the speed very high. We'll just take a look at the maths. Sorry, I've gone a little bit ahead of myself. This is the formula. I'm sure you remember your Greek letters, omega and tau. Omega is for speed and tau is for torque. Hope you can see now why we learnt Greek letters back in semester 1. We just do a little bit of manipulation, divide both sides by omega and flip it around, and now we get this. So now we can see that torque and speed have a reciprocal relationship. So what this means is, now what you can do is change the speed of the drill with the trigger or whatever, but essentially with a drill bit, you can either, or with a cordless drill, you can either have speed where you're drilling something really light and there's very little torque required. But if there's lots of torque required, that's going to reduce the speed. So often you'll hear a drill as it goes into a wall, you'll hear the speed reducing and the kind of torque increasing. So torque is driving force. Obviously, if you're trying to drive a drill bit through a concrete wall, you're going to need more torque. As a result, the speed of rotation will have to reduce. So doubling the speed halves the torque. That's drilling through something light. And similarly, if we halve the speed, that doubles the torque. So it's just another example of that kind of, you can have one or the other, but you can't have both. Speed and time, as I mentioned in the last lecture. I won't get into it in as much detail. So if you double your speed, that halves the time taken for a journey. Or similarly, if we halve the speed, that doubles the time taken for a journey. So the main thing to realize with these reciprocal relationships is when your input variable is below the line, this reciprocal relationship takes place. When you reduce the input, that increases the output, and vice versa. Just the only thing of note here is that time is an output in this case. When we change the speed, because we can't change time, but we can change the speed of a vehicle. So in this case, speed is the input and time is the output. It's one of the few cases when time is the output. Say if you're painting a wall, the time taken to complete a task and the number of workers. So the more workers you have, the less time it takes to complete a job. And we all know this. Time is also an output in this scenario also. So that, folks, finishes us up for this one. So thanks again for listening, and just keep an eye on those practical examples, because I'm always going to be looking for those to show that you understand, you know, what does the equation look like, what does the graph look like, and where does this function apply in real life. They are critical learning outcomes for each function. That's why I have those little slides at the start of each lecture. I think the second slide of this lecture was typical. You'll look back through the other cubic, quadratic, linear, and you'll see similar slides. I will always be testing your knowledge of those. Okay, so I'll stop talking now, folks. Thanks again for listening, and we should chat to you in the next lecture.